So in this video, let's talk a little bit more about acceleration and what acceleration means when something is moving in circular motion. So imagine here we have an object in circular motion over in the top right corner. At some earlier time, it's in the red location, and at some later time, it's in the blue location. So in other words, it has an angular, it has a angular velocity, which is counterclockwise, going counterclockwise around the circle. All right. And let's say furthermore, everything in this video, we're going to assume that the object is moving at constant speed, which also means constant angular velocity. What does the acceleration look like for this object? All right. So first of all, let's think about the velocity, because the acceleration tells you how the velocity is changing. So in the red state here, the velocity would be like this, tangent to the circle. Get rid of this to make, get rid of that to make a little bit of space. Okay, so this is the velocity initial. And then in the blue state, now the object's velocity is still going to be tangent to the circle, but now it's in a different direction. So it'll be like this, final velocity. Okay, so the initial velocity is in red, the final velocity is in blue. So notice something. If I grab those initial velocity and final velocity vectors and put them on a little coordinate system to the side here, okay, we've got the initial velocity is pointing something like this. So that's just copying down the initial velocity. I'm just moving it to a new coordinate system so I can see it better. And now the final velocity looks kind of like this. So there's my final velocity. You'll notice which way did the velocity direction change in? How is the velocity changing? So the direction of how the velocity is changing there would be a vector that goes from the initial velocity to the final velocity, something like that. So in pink, this would be delta V, the final velocity minus the initial velocity. And I want you to notice the direction of the final velocity, of the change in velocity. Notice how, like in this case, it's kind of down with a little bit of left. If we were to take that delta V and move it back into the top right picture, it would look something like this. And not surprisingly, it would be perpendicular to the initial velocity vector. That's because I'm assuming here that the speed of the object is constant. So if the speed is constant, that means there can't be any component of the acceleration which is in the same direction or opposite direction of the velocity. The acceleration has to be perpendicular to the velocity, because remember, the acceleration points in the same direction as delta V. So that would be the direction of the object's acceleration. And you'll notice where that vector points to is back towards the center of the circle. And that's a general property that is true throughout the object's motion, that the acceleration vector, if it's moving at constant speed, the acceleration vector is going to point back towards the center of the circle. Okay, so if the object is moving at constant speed, which by the way, that is referred to in the world of circular motion as uniform circular motion. If you see the term uniform circular motion, that means circular motion at constant speed. So if the object is moving at constant speed, then the acceleration points toward the center of the circle that the object is moving in. Furthermore, the acceleration is perpendicular to the velocity at all times, and that's how the object can be moving at constant speed. But I want to emphasize, if the object is moving in a circle, acceleration cannot be zero, because an acceleration is required just to keep the object moving on a circle. Because zero acceleration, it would have to be moving in a straight line. So by virtue of the fact that it's moving in a circle at all, it has an acceleration. And that acceleration that it has, even at constant speed moving in a circle, points back towards the center of the circle. This acceleration is called centripetal acceleration. So centripetal acceleration is the acceleration which is there even at constant speed. When an object is in circular motion, it points back towards the center of the circle. So the direction of centripetal acceleration is toward the center of the circle. And the magnitude of the centripetal acceleration, I'm not going to try to prove what it is here. I have something in the notes if you're curious, but the way it shakes out is that the centripetal acceleration magnitude is equal to the speed of the object squared divided by the radius of the circle that it's moving in. Or if you prefer rotational variables, it can also be written as the angular velocity squared times the radius of the circle the object is moving in. So that's how you handle the acceleration when you are in uniform circular motion. You know that it is a centripetal acceleration. What's interesting about this is, previously in the course, when we solved F equals ma problems, generally we knew a lot about the forces and we were solving for the acceleration. But in this case, a lot of times in circular motion problems, you actually know a lot about the acceleration, because you can figure out a lot about the acceleration just by knowing about the circular motion that the object is in. So oftentimes in this business, you might now be solving F equals ma problems where you have to realize certain things are true about the acceleration and then plug into the ma side of the equation and work your way backwards to the forces.